Welcome to Unit 14, where we explore the classification of elements and the foundation of the periodic table. Classification of elements is the process of grouping them based on their similarities and differences. The periodic table is the chart created by arranging these elements based on those characteristics. Dmitry Mendeleev is widely recognized as the father of the periodic table, having developed a system to organize elements based on their properties. Mendeleev's periodic law states that the physical and chemical properties of the elements are a periodic function of their atomic weights. Mendeleev's table was groundbreaking, as it successfully accommodated all known elements at the time, provided a basis for modern periodic law, left gaps for undiscovered elements, and helped predict the properties of many elements. However, the table had defects, such as issues with anomalous pairs, the grouping of chemically dissimilar elements, the placement of isotopes, and the lack of explanation for electronic arrangements. The modern periodic law improved upon these concepts, stating that the physical and chemical properties of elements are a periodic function of their atomic number. Modern theory corrected many of Mendeleev's issues, including the placement of hydrogen, isotopes, lanthanides, actinides, and the classification of alkali and coinage metals. This table highlights key differences between the original and modern approaches, specifically regarding atomic mass versus atomic number and the organization of groups and periods. The modern table provides a clear structure for locating hydrogen, metals, nonmetals, metalloids, rare earth elements, and inert gases. Here is an overview of the periodic table, showing how various elements are classified and positioned today. This chart demonstrates a simple way to identify the atomic number and approximate atomic mass for elements 21 through 30. The Aufbau principle explains that electrons occupy atomic orbitals in order of increasing energy, starting from the lowest energy level. Electronic configuration is formally defined as the specific distribution of electrons into the various orbitals of an atom. S-block elements are divided into Group 1, or alkali metals, which have 1 electron in their s orbital, and Group 2, known as alkaline earth metals, which have 2. The p-block, spanning columns IIIA to VIIIA, contains 35 diverse elements. These elements, excluding helium, feature valence electrons in the p orbital. Within the p-block, you will find a mix of metals, nonmetals, and metalloids. This region also contains the halogens in Group 7 and the noble gases in Group 8. Next, we focus on the D-block elements, which form a significant section of the periodic table. D-block elements are known as transition elements. They are named this because they exhibit behavior that transitions between the highly reactive metals of the S-block and the less reactive elements of the P-block. The F-block contains 2 distinct series. Lanthanides include atomic numbers 57 through 71 and are generally non-radioactive, with the exception of promethium. The second series, the actinides, consists of elements with atomic numbers 89 to 103. These elements are primarily characterized by their radioactive nature. F-block elements are often referred to as inner transition metals. They sit in the 6th and 7th rows, effectively separating the S and D blocks. To understand the periodic table further, we must look at the characteristics of periods and groups, including atomic radius, valency, and reactivity. This chart illustrates the general activity of metals across the periodic table. A key trend to observe is that as you move down groups 1 and 7, the reactivity of the elements tends to increase. We will now begin exploring atomic radius, which is a fundamental property of elements. Reactivity is defined by how easily an atom achieves stability. Potassium is more reactive than calcium because of how easily it can reach this stable state. In summary, metallic reactivity increases down a group because larger atoms lose electrons more easily. Conversely, non-metal reactivity decreases down a group because larger atoms have more difficulty gaining electrons.